Section 6.1 looks at ratios, proportions, and the geometric mean. This is an introduction to Chapter 6, which is on similarity. Start with a couple terms we need to know. The term ratio. And when we think about ratio, we're going to think of that as the ratio between two numbers, the ratio of A to B in this case. Now we can represent that ratio a couple ways. We can say it's the ratio of A to B. We could write in this form, or we could write it as a fraction, which would be A over B. So that really gives the idea any fraction is representative of a ratio. A to B, 1/2, 3/4, they're always going to be a ratio. Typically, we'll use them as a fraction. If it's not written as a fraction, we'll change it that way. A key thing to note for ratios is they need to have the same units. For example, if I have the ratio of 5 inches to 1 foot, I'm not going to leave it as 5 to 1 ratio. I'm going to change it so it would be 5 inches over 12 inches. That way it's the same units and represent it better. Same thing goes feet to yards, meters to centimeters. Always want to change it back so it's the same units. Now a proportion is an equation that states two ratios or fractions are equal. So, a ratio is a fraction, a proportion is a fraction equal to a fraction. So if I said A over B equals C over D, that would be a proportion. I have the ratio of A to B and the other ratio of C to D. I set them equal. Now, if we solve with proportions, and we're going to see that quite a bit in this chapter, we're going to use the cross product property. And you may remember this from algebra. And this would be where I would have A over B equals C over D. And I can take that and multiply what the diagonals are. So it would be AD equals BC. So maybe in this case I know A, B, and C. I need to solve for D. When I multiply, I'd then be able to solve for D, get it by itself. So cross product is what we use. You also have another term in this section, which were the extremes and means. We're going to see how means is used a little bit later in the section, also later on next chapter it comes up again. But for identifying the extremes in a proportion will be A and D, and the means will be B and C. Again, we'll get to the means, particularly the geometric mean, in a moment. We don't really use them much to identify. Geometric mean will be a term in itself, but it's good to know where they come from. So let's look at some practice with some proportions. So if I have 6 over x equals 3 over 2, this is where I know 3 values and I want to find the missing one. So we can do cross product where I multiply the diagonals. So I'd get 3x equals 6 times 2, or 3x equals 12, and x equals 4. If I look at this proportion, I do cross product, I would have 3 times 4p equals 1 times the quantity 2p plus 5. After I do cross product, I'm just going to multiply everything out. I get 12p equals 2p plus 5. Subtract 2p from both sides, I get 10p equals 5. Divide both sides by 10, and I get p is 5 over 10, which is just 1/2. It's okay, it's a fraction, doesn't mean it's wrong. That's the value I would need to make it work. Now let's check to make sure. So let's plug this back in and see how it actually does work for us. So if I plug that 3 in, or plug the 1/2 in for p, I get 2 times 1/2 plus 5 in the denominator for my first fraction, and 1 over 4 times 1/2 for my second ratio becomes 3 over 1 plus 5, which is 3 over 6. And the right side becomes 1 over 2, which is 1/2. And I can see 3/6 is equal to 1/2, because if I reduce 1/2, it is 1/2 itself. So as we find these values in proportions, we're really finding the value that makes it work. Okay, we keep going here. I have 1 over c plus 5 equals 3 over 24. So I'm going to multiply 3 times c plus 5, and that's equal to 24, or 24 times 1. Whenever I have to distribute, make sure you multiply both terms, 3 times c and 3 times 5. So I get 3c plus 15 equals 24. I subtract 15 from both sides, and it looks like I have 9 left over, so 3c equals 9. And I get c equals 3. Quick check, if we plug this back in, we'd have 1 over 8. 1 over 8 and 3 over 24 would be equal fractions, particularly if I reduced that 3 over 24. And that's really the goal. Can we get equal fractions? Last one, cross product. 2 times 1 plus 3b equals 5 times 4. Distribute again. Be careful. Students seem to forget that second term a lot to multiply it. So it's 2 plus 6b equals 20. If I subtract 2 from both sides, I get 6b equals 18, and b equals 3. Now let's go back up to this first one real quick, and just see sometimes there's another method. When I'm adding these, like I have for these other ones, doesn't quite work. But if I just have something like 6 over x equals 3 over 2, sometimes we can kind of just shortcut and find a way to get it without having to do cross product. Because if I notice, when I check my answers, like here where I had 3 over 6, or up here where I had 1 over 8, and I found that actually I could reduce and get the same fractions. Let's keep that in mind here. So if I took 6 over x equals 3 over 2, I want to take this 3 over 2 and I want to apply it to this 6 over x. So I want the value that would make the fractions the same, and that's that value for x. So if I took 3 to get to 6, I multiplied it by 2. If I did the same thing to 2 and multiplied it by 2, I would get x equals 4, which is what I found up there. So at times when it's just a basic proportion, and we don't have the addition like we had in these, we can just multiply that fraction to equal something. We got that 3 to match the 6, and then the bottom value would be the same. Something to keep in mind if it works for you. It's sometimes a shortcut on these proportions. But otherwise, cross product is our good old standby method. Now next we have the geometric mean. And the geometric mean, so we're going to define this as the geometric mean of two positive numbers and these positive numbers are going to be a and b, is the positive number x such that we get a over x equals x over b. Really, this is just a proportion we've had. But now instead of two different values in those means, those x's, it's the same thing. Now, let's take that idea of cross product we had. If I took this and did cross product, I would get x times x equals a over a times b. Well, x times x is just x squared equals a times b. Let's clean this up a bit. Let's take the square root of both sides and move it over. So now I get x equals the square root of a b. Normally when we take the square of both sides, we may have to worry about that plus or minus, but the fact we're looking for positive values, we're not going to worry about that. We're just going to say x equals the square root of a times b. So this is going to be the rule we're going to use for geometric mean. If they ask for the geometric mean of two values, we're going to multiply them and take the square root. Kind of like with what we have down here, where find the geometric mean of the two numbers. 2 and 18. So my geometric mean is the square root of 2 times 18. If we do that, we get the square root of 36, which is just 6. So geometric mean of 2 and 18 is 6. And if I set this up back in this proportion we had, well then I would have 2 over 6 equals 6 over 18, and both of those we reduce to be 1/3. So it's that value that fits to make this proportion true. Next I have 4 and 25. So the square root of 4 times 25. This one I can multiply and see it's 100. Square root of 100 is 10. So my geometric mean of 4 and 25 is 10. And just a quick look, be 4 over 10 and 10 over 25. Those would both reduce to be 2/5, so I can see that that does work. Okay, those are nice because they were perfect squares. They simplified nicely. Sometimes we have to write it in simplified radical form. So now I have x equals the square root of 2 times 25. Now I could put those together and see that's the square root of 50, or radical 50. But let's leave it in this broken form to see how we can actually break it down and find simplified radical form a little quicker. 2 times 25 is 2 times 5 times 5. If I have two 5's inside of a radical, I can put those together, take them, and put them outside my radical. So I'm left with 5 on the outside, radical 2 on the inside, so my geometric mean of 2 and 25 is 5 radical 2. For x equals 16 times, or x equals the square root of 16 times 18. Let's take that same idea. I notice 16 is a perfect square, so that's 4 times 4. 18 is actually 2 times 9, or 2 times 3 times 3. So I can take a 4 out, I can take a 3 out. Radical 2 left, it becomes 12 radical 2. Now let's finish up with a couple examples where we now take this idea of looking at ratios, or maybe proportions, and solving with them. So I have an example where I'm looking at the area of a room is 4,320 square feet, and the ratio of the length to its width is 5 to 6. I need to find the length and width of the room. So we have a room here. Inside the area is 4,320. I have my length, I have my width, and I know that's a ratio of 5 to 6. Now that doesn't mean the length is 5 and the width is 6. That's the ratio. So if this was only 5 units, then the width would be 6 units. But we can see that, well, 5 times 6 is not 30, or 5 times 6 is 30. That's not 4,320, so that doesn't work. But we want that idea we can keep multiplying up and find bigger values. So what if I said this is 5x and this is 6x? Because now if the length is 5x and the width is 6x, I can put multiples in there and see. So 5 and 6 would work, 10 and 12, 15 and 18, 20 and 24, and keep seeing eventually whatever values I'd have would multiply to give me the area. So I'm going to call it 5x and 6x is my new ratio. So I know the area of a rectangle, or this room in this case, is length times width. Area I have is 4,320. My length is 5x. My width is 6x. So 4,320 equals 30x squared. If I divide both sides by 30, I get 144 equals x squared, and the square root of both sides leaves me with 12. So that 12 is actually that multiplier I would need to get these values to still hold the ratio and for the area to be equal to it. So that means my length is going to be 5 times 12, or 60, and that would be feet. My width is going to be 6 times 12, or 72 feet. Now, check real fast. Is 60 times 72 4,320? If it is, we found the right value, we're good, and we found the correct, and the ratio held, because 60 to 72 in the end would still reduce to 5 to 6. Now, let's think we still have a room, but now this room has a perimeter of 48 feet. Now, perimeter is different than area. Perimeter means that distance around. Now, our length to width is 7 to 5. I still want these ideas of multiples here, but I have to go about it a little differently because now it's perimeter. Perimeter, we know, is adding up the distance of all the sides. So it's length plus width plus length plus width. So let's still put those x's on it. 7x, 5x, 7x, 5x. Because we could see if I did 5 and 7 and 5 and 7, that would be 24. Just if x was 1. That doesn't give me 48, so it doesn't work. So we need to find that multiple that would work. But the fact it's 24, do you see what it could be? What that multiple will actually work? Let's see. So perimeter, we could write it a few different ways, but it's 2 times the length plus 2 times the width, or we could write it as length plus width plus width. Either way, doesn't matter, whichever way you're more comfortable with. But 2 times 7x plus 2 times 5x gives me 14x plus 10x, which is 24x. Now we know our perimeter is 48. If I divide 48 by 24, I get x equals 2. So it turns out our multiplier was 2 there to keep the ratios together. That means my length is 14, my width is 10. If we check real fast, 14 and 10, if I added those up and then added them again, 10, 14, 10, 14, I would get 48. So 14 feet and 10 feet. Now last problem, we're going to take the same idea of the ratios, and we're now going to look at angles in a triangle. So we do get to some geometry here. I know you guys are missing the triangles. Want to think they're getting left out, but we can look at them here with the ratios. So I'm looking at the angles in a triangle, and they have the ratio of 1 to 3 to 5. So I need to find the measures of the angle. It's like our length and width. Looking for that ratio still to hold, but if I look, I know these aren't the angles. 1, 3, and 5 are not the measures of the angles. Because, well, we know that if you add up all the angles, let's label them here, A, B, and C, the measure of angle A plus the measure of angle B plus the measure of angle C is 180, and these are definitely not 180 right now. So we're going to put the x on it, because we want that ratio to hold, but we realize we're going to multiply to make these values bigger. So I have 1x plus 3x plus 5x equals 180. Put those together, that gives me 9x equals 180. Gives me x is 20. So I now take my 1x